Thank you, Rafael. Thank you, everyone, for joining. I hope you all at least got a seat. We'll talk about today safety, especially for the automotive domain. Before we do, I'll give you a short introduction for those who were here last year. This will be repetitive. For those who see me for the first time, I hope it's going to be interesting. Then we'll talk about safety, how we define it in the automotive industry, as well as the challenges that we face currently and for the future. So let's talk about the company that I work for, TTTech. We're based out of beautiful Vienna, Austria. I founded 20 years ago as a spin-off from the Technical University and have been building safety-related systems ever since. First product was the TTP network, so time-triggered protocol network for the 787 Dreamliner. Hence the name TTTech, so the time-triggered technology company. We built this time-triggered protocol which replaced the CAN bus on top of the 787 and helped Boeing to reduce the integration time of those 80 electronic subsystems from almost 4 to 5 months down to just 2 weeks. So a significant gain in time in a critical path for a very safety critical system, because it's clear all the electronics you need when you fly in the plane and you don't want to lose them across the Atlantic. Now, another American company approached us a little bit after because they heard about the success with Boeing. They knew that Airbus for the A380 used the same systems also to control the cabin pressure system. And they said, you know, we're decommissioning the space shuttle. And we're looking for a reliable network that we can connect all of the sensors, so backbone system. But the TTP that you have is not enough bandwidth. We need it Ethernet-based. Can you do a gigabit Ethernet-based, but time-driven? So clearly we said yes as a young company, and together with NASA, we developed a standard that is aerospace compliant, but also compatible to our networks that we all have in our offices today. And we made a product out of it, and very proudly it went into space and safely returned to us 3 years ago. And the Ariane 6, so the European Space Agency, they're using the same technology for the next generation space launches, the Ariane 6 program. Why am I telling you all this? First of all, it's interesting, but all of this, so the learnings that we took, how to build safe systems for the aerospace industry, how to integrate 80 different subsystems, and technology developed for space is what made it possible to have the ZFAS, the first street-legal, level-3 automated driving system in the world, developed for Audi together with Audi. The system went live last year, and here we applied learnings from the aerospace industry on how to integrate systems. 35 different applications from 15 different vendors went into one single ECU. Quite a novelty in the industry back then, overcoming a lot of challenges, also dealing with components that weren't designed for the automotive industry, try to make them safe. So this is where our expertise comes in. And the result of that is the product that we call MotionWise. We'll talk about it later a little bit. For now, I just want you to take this away. This is where we come from. So now let's talk about the topic at hand, safety. And how do we achieve it in the automotive industry, especially when we talk about automated driving? Before we do, let's define what is safety. We'll take the definition from the ISO 26262 standard. The ISO is a set of standardized processes and methods that you apply when you build electric or electronic systems for the automotive industry. And the standard says, well, safety is the absence of unreasonable risk. What we want to achieve in the automotive industry is functional safety. So we don't look into radiation, heat, or smoke. We look into functional safety when designing these systems. And functional safety, according to the standard, is the absence of unreasonable risks due to hazards caused by malfunction behavior of these set EE systems. Now, you see, by the definition, the standard already says, you know, there is no zero risk. There always will be residual risk left over. But we try to design the systems as safe as possible. Why do we do this is probably clear. We'll talk about it in a minute. Let's do a practice round. If we have some safety engineers with us, on the picture, do you see a risk that we need to mitigate? We could do. No seatbelts, very good. Usually when we do these talks within the company, the first thing is the arm. We say, well, the arm is not part of the systems, plus the lady is looking ahead so she knows when something is coming and take the arm back in. The seatbelt is a different issue. People should buckle up, you all know this, and one of the systems that you all have in your cars probably is this annoying noise that it makes if you forget to put the seatbelt on, but it's there for a good reason, because it's not only you that needs to be safe, but anyone else in the car needs to be safe as well. Think of a crash situation with somebody sitting behind you who has not been buckled up. He becomes a projectile that could straight hit into your seat and hurt you as well. So when you get into a car, ask everyone to put the seatbelt on. Another thing, beautiful old car. Do you see something missing here that modern cars have? Yeah, the roll bar, correct. So in a situation where we all don't want to be going in, the car lands on its top and would not be stopped by a roll bar that you usually have in modern cars. So this is how we look into systems. We think about possible situations that may occur, hazards that may stem from these, and try to design the automotive and the electric systems according to this. So there's a little practice done. Let's look into some, I would call them guiding principles, famous words according. One, you all know, Murphy's Law. Murphy, American aerospace engineer, designing safety systems. So if we design systems, do we always think of the worst? No, but taking this as a leading example, think about, okay, looking into a system, what could go wrong? And if it goes wrong, is there something else that if it goes wrong, it gets worse at this point? So this is how you look into it. Now, more relevant for the automotive industry, especially when we talked about automated driving, is the second one, and I like this very much. Increasingly, people seem to misinterpret complexity as sophistication, which is baffling because the incomprehensible should cause suspicion rather than admiration. I like this so much because, first of all, it's straight to the point. And then if you think about how do we achieve level 4, level 5 automated driving, is by using artificial intelligence, machine learning. So basically, machines that teach themselves how to steer and maneuver a car safely between humans. And to make the system safe is the real challenge, because you can't always foresee why the system takes certain decisions and why not. So we talked about safety being relevant because you all want to be safe and arrive at home, but also consumer acceptance is another thing. This technology that we're talking about can only be successful if there's the market for it that accepts it. The same problem was true in 1850 when the elevator was invented first. People were very afraid of getting onto the platform because it could fall down. The rope might rip and plummet them to the ground and die. So the inventor, Otis, thought of a simple but very effective safety mechanism. He said, okay, the hazard is the cabin falling down. I need a sensor to detect this. The sensor would be pressure on the rope. As long as there's pressure on the rope, everything's fine. Now, if the pressure is suddenly gone, the rope rips. I want an actuator, a system to take over and secure the elevator in place. So connected to the rope, he had a metal plate that once released would expand and hook onto the teeth that you would place along the elevator shaft, thus holding the platform in place. And since presentation is everything, he went on the platform, stood there, had somebody above him cut the rope, and the elevator kept in place. And now this is a drawing depicted in 1853. You can see by the crowd's reaction, people were baffled, but they increasingly put trust into the system. So showing that the system is safe creates trust and creates consumer acceptance, something that we all want to achieve by creating these systems and make automated driving a reality. Good, with that, a few words. Let's talk about the topic at hand, safety, and the ISO standard and how it's applied. Now, as said before, the ISO standard is a set of standardized processes and methods that you apply when you build electric and electronic systems. You do these because you can compare systems that have been built all over the world and know if they're built accordingly to certain requirements and standards and how safe they might be. Now, I don't want to take you through all of this. I just want you to see that the standard applies to the entire life cycle of the product. So from early concept phase all the way to production. You see it's covered by a V-cycle. So you do requirements and you later validate and test them. You do the same for all the hardware and all the software components in smaller V-cycles. We're not going to go through all of these, but I want you to take away from the next 10 minutes the essence of what the standard holds and be familiar with some of the terms used in it. So when you talk to a colleague the next time about the automotive industry, you could be a little more knowledgeable as well. And for that, I hope you're all here today. Now, in the essence, the processes and methods applied are there to create a functionally safe system. And according to the standard, a functionally safe system is achieved once you met all the safety goals. So first step is, how do we get to the safety goals? We define a system, which is called an item by the standard. So any system and its neighboring counterparts that it interacts with is our item that we want to look into. Now that we have the item, we define hazards. So we identify hazardous events that could occur for the system at hand. So you list all the potential threats. And once this is done, you go about assigning an automotive safety integrity level to each and every single item. So this ASIL you assign to the hazardous events. Now, ASIL is a term that layers into different criticalities, basically. So you have on the very low end, the QM, where the standard says, well, for an event that is just QM, we don't need to apply any specific requirements, but the quality management system of the company that produces these systems should be sufficient to mitigate any risk. For the rest, the ASIL basically expresses the level of risk reduction required, methods applied to avoid the hazardous events happening. How do we go about this? In a simple hazard and risk analysis. And we'll do this now step by step so you get a feeling for it. So this HARA, short for hazard analysis and risk assessment, has 3 dimensions. The first one is you look into the event and say, how severe is it if it happens? So somebody involved in such a hazardous event, could he be lightly injured, or could the event even be fatal to the person? Second dimension is your exposure. So the possibility of you coming into the situation where the event could occur. Giving you an example, if you say, okay, the hazardous event could occur when the car is stationary at a red light. So you parked at a red light. You all here that came by car today probably stopped at 1 or 2 red lights. So in a situation like this, it's highly likely, so high. A different one would be you stopping, being stationary at a railroad crossing with an oncoming train. Less likely, doesn't happen so often. There's also additional safety mechanism that should you prevent from even crossing onto a live railroad. Now, the third dimension is the controllability that we look into. So how easy is the event to be controlled by a normal driver? Is it simple, normal, or is it difficult to be controlled? And where all of the 3 dimensions meet, you can see in the table, you get the assigned ASIL levels. Now, where all the extremes meet is ASIL D. So the highest requirements usually are for the most severe and most difficult to control hazards. Since this was quite quick, let's take an example. And our item here, our system, is electric single motor. So basically electric car, how it's driven. You know, it's different from the combustion engine. Usually you don't have a clutch. And you go through the system design and you say, okay, there's one function in there. The intended function is to apply positive torque. So put your foot down on the gas pedal and accelerate. One possible malfunction of the system could be that torque is applied by the system itself, even if not requested by you, the driver. Now, in a situation, as we said, you stopping at a red light, standing front row, with traffic coming through in the intersection, your car suddenly accelerates. Now, the severity of an incident here is quite high because either you run into the passenger door with somebody sitting there, or you get hit by oncoming full-speed traffic on the driver's side. So clearly, injuries could be fatal at this point. Now, again, the exposure, so how likely are you to come into a situation? Stopping at a red light, everyday situations are very high. And the controllability of you, or your ability to control the car, when it suddenly accelerates out of the blue into oncoming traffic, it's probably very difficult. Hence, we come to an ASIL D rating for this specific hazardous event of happening. Now that we have defined the ASIL, we assign a safety goal. Usually these are quite simple requirements that say basically torque can only be applied when specifically requested by the driver. The safety goal then should help to avoid this hazardous event. Sounds simple. In reality, implementing it can be quite challenging. Now, just to give you a different example, same system, different malfunction, different situation, has a different severity, leads to a different ASIL, but you also apply a different safety goal here. So basically, this is how you go about. You go through the system and think about all the things that could happen, then you assign an ASIL, and by each hazardous event gets a safety goal assigned as well. Now that you have the safety goal, you continue through the process by assigning requirements to reach these safety goals. So you basically have a safety goal, put down a requirement. When you have the requirement, you allocate it according to architectural components that you choose. So architectural components are software, hardware systems that you implement in order to reach your goals. This all, again, is connected to the automotive safety integrity level, the safety. So you have a safety goal that describes the safety requirements. They inherit the ASIL level and thus form the subsystems that you need. And all of this then goes into the technical requirements, the system level requirements, and the overall system is created in this way. So now you can see that starting this process at the very beginning before you start production is essential, because if you do it reverse, you might end up having to pick components that do not fulfill the safety requirements, and you have to redesign your entire system. This is why you do this very diligent process from the very beginning on and walk through it. Now, in the final steps, you produce a system, then you verify that everything has been done according to your requirements, the safety goals can be met, and you also do conduct a functional safety audit, usually by a third party, to show that you actually have done the entire process and have been consistent with the methodologies and rules applied by the ISO standard. So this was the very quick and condensed and simplified view. The entire process is quite cumbersome, but it's very important to catch all the little mistakes or hazardous events that could occur from such complex systems. Now, where do we have different systems? For instance, at the very top left, you can see infotainment audio has a very low ASIL rating. Why? Well, clearly because if these systems fail, it's annoying at best, but it's not life-threatening. For instance, on my way here, the navigation system failed me, so I had to pull over, restart it, and could continue to drive. So there's nothing that was major. But the systems we want to talk about lower, below the car, that interact with your driving, so the steer, brake, lateral controls, as well as power, they all have a very high safety rating. So these systems that we want to build when we talk about automated driving, they do have to be compliant to the highest possible safety requirements that the standard has. So we'll talk about the challenges that we have with today's systems. We'll talk about an unfortunate example that has happened that is well covered, and think about together what could have been done from a design perspective to maybe avoid or at least mitigate the risks coming from this. Now, to remind everyone, there's different automotive levels that we have. First, we'll be looking into level 1, level 2 systems that are out on the road today. And level 1 and level 2 are only assisting you as a driver and not actively engaging and taking away tasks from you. So in level 1, level 2, you are always the one being in full control of the car. Level 3 is a small paradigm change. So a system that was built, for instance, for Audi and released last year. Here, under certain conditions, for certain situations with certain speeds, the driver can give over control to the car. The car will maneuver the car as long as necessary or as long as the situation doesn't change. Now, if the car detects a situation changing, it will hand back control to the driver. Hence, the driver is not always responsible, but he is always the backup system of the level 3 system. Level 4, level 5, here the driver is not taken into consideration anymore as a backup. Here, the system should be designed in a way that they are providing fail operational ability. We'll come to that in the later part of the presentation. Now let's focus on level 2 system. And I picked one that is here from the Bay Area. It's well documented. It's the Tesla Autopilot. So let's take a look into some of the snippets from the user manual and what it says about its system. You see here, over and over again, it's mentioning you should have your hands on the wheels. Oh, something is missing. Sorry, I don't know. That got lost in the presentation. So yeah, there were highlighted parts. I'll give you the brief recap. Hands on the wheel at all times. It's your responsibility as the driver to control the vehicle at all times. You should adapt your driving to the conditions, and the system should only be engaged under certain environmental conditions. These environmental conditions are clearly specified in the user manual, saying you should only be used in expressways, highways with limited access possibility. This means only on streets where you have an on-ramp and an off-ramp, the autopilot should be engaged because it's limited to the use in these situations. Now, in 2016, an incident happened where the Model S from Joshua Brown ran into the semi-trailer at full speed while autopilot was engaged. This unfortunate happened. Joshua died straight away, and later the investigation started, and I'm taking all the information from the official report. Now you can see the car ran into the semi, and the way the car works, the way it perceives its environment is by two sensors. It's a front-facing camera that works with light, and it's a radar system. The light, so the camera that works with light, had a good visibility on the daylight situation, and even at night probably would have worked because there were reflectors along the line of the semi. Now, the radar is a different story. It's a different technology. It works with radio waves that needs a reflection to return to the original antenna, that is the sensor, to be able to perceive the environment. The problem in this specific situation, I talk about Murphy's Law, the semi was angled in a way that the radar waves were deflected from it, so away from the car. So even if the radar waves would have hit it, it would have been deflected straight away, and the radar wouldn't have been able to see the huge obstacle in front of it. Why is this so important? Because if you look into the system setup as safety engineers, you see that there's the radar in the grille and the camera on top. These are the two sensors the autopilot uses. The ultrasonic radars, they're just for parking, so near field communication. Now, the autopilot uses camera and radar. The autopilot and also another system, the automated emergency braking system that all modern cars have, they both need feedback from these two sensors to say there is an object in front of us, initiate a maneuver or initiate automated emergency braking now. Since the camera detected it, but the radar probably couldn't because of the angle from the semi, no maneuver was engaged, and the car ran with full speed into the semi. Now, to be very fair, not only did the system warn the driver about it, but I mean, the manual warns the driver about it not to use it in these kind of situations, but also no other system that was out there in 2016 would have been able to detect this. So the technology wasn't ready yet to perceive this crossing traffic. Hence, the manual also said, don't use it in situations where somebody could be crossing in your line of sight because the system might not be able to recognize it. Now, let's take a look into what happened before the crash. And I want you all to think with me about possible systematic safety fails that we could have implemented in the system to avoid it. Now, what you see here is that for the driving cycle of 40 minutes, nope. There we go. The driving cycle took about 40 minutes until the crash happened. In gray, what you see is the autopilot being engaged. So for the majority of the time, roughly 37 minutes, the autopilot was engaged. The other thing that you notice probably is the little yellow stripes and the little flash symbols. those are visual and auditorial signals telling the driver to put his hands back on the wheel. Because the way the system perceives that the driver is actually in control of the car, has its hands on the wheel, is that it detects torque applied to the steering wheel. Now, what you see is the system visually warned 7 times, and with the auditory signal 6 times the driver to put his hands back on the wheel. So 6 times before the incident happened, over and over again, the system was detecting that the driver wasn't being consistent with the instructions given by the user manual or wasn't adhering to the limitations of the system. What you also see is the little green dotted line, and this is when he puts his hand on the wheel. Now, if you read the report, which is in source here, and go through the 60 pages, you will come across the section where it mentions how long he had his hands on the wheel. Out of the 37 minutes where autopilot was engaged, where he should have had his hands 37 minutes on the wheels, 25 seconds the system detected his hands actually being on the wheel. So clear misuse of the system and neglecting of the instructions given. What you also see is State Road 24 and US 27. Those are both roads, if you look it up, that are not part of the specifically described boundaries and environment that the system should be able, is able to work in. So it was used outside of the limitations again. The problem that we have is that we didn't enforce this. So by law, think about, you all identified the buckling up, and you all know the system can be very annoying if you don't listen to it. In this instance, it seems that the system is not persistent enough in convincing the driver, not strict enough with the driver, and forcing him to be in control of the car. So one of the things that you probably think of is, let's be more annoying. Let's be more strict with the driver and enforce him to put his hands back on the wheel. The driver was engaging with the system, so he was accelerating as well, yeah? Yeah, that was also part of it. Yeah. Yeah. It's a good point from the audience that he's also exceeding the speed limit given, and the car would allow this. So these are also things that in the system design, in the safety design, the safety engineers should have thought of and said, okay, we prohibit use of the system exceeding the speed limit. Now, if you say, okay, maybe systems, they changed and they don't know if the rules are different, still, what they can do, because the car has a navigation system, has a GPS signal, you can clearly mark the roads where the system can be used on. And these roads wouldn't have been on there. So you could have, by system design, restricted the use of the autopilot to roads that are deemed safe to use these functions. So thus, controlling the driver and helping him to stay safe and everyone around him. So this is basically the essence also that we have identified from the report that was given by the National Transportation Safety Board. Causes of the crash were, of course, the truck driver not yielding onto oncoming traffic, the over-reliance of the driver into the system, and the system design itself, which wasn't strict enough, wasn't enforcing its own rules. So there was a huge discrepancy, inconsistency between what the system was designed for, what the warnings in the user manual clearly indicated was not allowed to be doing, and what the system would be allowing the driver to do throughout the driving cycle. The board came up with several recommendations, which some of them were implemented as well by Tesla later on, but still might not be strict enough. Anyway, the idea here was not to put blame, but to give you a feeling of how these systems should be designed and how we should think about the systems when we design them. Because unfortunately, we as humans are very prone to error, and we will misuse these systems the first chance we get them. So by design, the systems should not allow a misuse in them. Okay, so level 2 systems, check. Let's talk about level 3, level 4, level 5, and the requirements as well as challenges that we have with these systems. Now, level 3 system, we said clearly, here the driver can give control to the car and let the hands off the wheel. So something that in certain situations like a traffic jam on a highway, so controlled environment, is possible today. One of the safety assumptions that we have to take here is that because the driver needs to be capable to regain control of the car in a specific time, here 10 seconds as an example, we need to monitor the driver. We need to make sure he's capable of actually engaging with the system and regain control in that time. Now, a camera that would do this, for instance, monitor the driver, would be a potential solution here. Level 4 system is a different story, because for the level 4 systems, what we have is that the driver is out of the control loop. The driver is not, by system design, identified as a backup system, because the driving situation might be too complex for him to take over in 10 seconds. So think of a high-speed drive on the German Autobahn freeway, complex driving situation with other drivers crossing and signaling. You will not be able to control the situation in a matter of 10 seconds, probably. So therefore, the system, and our safety assumption should be that the system is designed with enough computational power and situational awareness, so sensors, that is redundant, and that is set up in a way that even if parts of the system fail, we can be driving. We can continue to drive. So an architecture that is very very capable of handling part fault of the entire system. Now for a level 3 system, this is an example of how it would look like, and we'll give you a short walkthrough. As we have a main node, which is to your left, we have a fallback node, which is to your right. These are two separate boxes, ECUs, connected to different power sources. Both of them are connected to the actuators, which the actuators should be fail operational as well, so they should be redundant, like drive, steer, brake, and all of these. So these are connected to one another, and they need to be fed information. So the sensors that we discussed, a LiDAR, a radar, a camera setup, also redundant, feeds in information into the system. That sensoric setup now feeds in a lot of information that needs to be processed extremely quickly. So multiple cameras, a LiDAR, a radar, several gigabytes a second if you just take the raw data. So you need a lot of compute power to be able to do this. The problem is the compute power, so the processors available for the automotive industry that are capable of handling this, they're not ASIL-D. And as described before, on the system level, we need to be ASIL-D compliant in order to gain customer acceptance, be safe, and also get authority approval. Now, what you can do according to the standard is you can decompose the system. So you can achieve operational ASIL-D functionality if you take components that are sufficiently independently designed from one another and deploy them side by side, so have a redundant setup. So basically here you feed the same information from the sources to two processors that both do the number crunching, do the sensor data, do the trajectory planning, do the path planning, and they then provide their recommendations to ASIL-D unit that is the checker. So this is a component designed for an ASIL-D system, usually not as compute heavy. So here it checks the results and maybe compares and then takes the decision where to go and sends the signal to the actuators. So what you see, the fallback node is not as sophisticatedly designed in the level 3 system as the main node. Now this is for several reasons, because the driver is still our fail-back system, and the likelihood of the main system failing for itself is rather low, so the exposure of the fallback node is really low. Therefore, it is allowed in this setup to have a fallback node with an ASIL level B. Plus, we do check the system, the fallback system, and random intervals to see if it's first still alive, it's still there, and if it's producing a sensible outcome. So this would be a level 3 system. Level 4, level 5 systems, which we're aiming for, they get more complex. You see level 1, level 2, fail, stop, so they just shut off and don't cause any more havoc. Level 3, we talked about. Level 4, you see we introduce on the fallback node a D-level component as well. And the level 5 systems is basically a full redundant setup, 2 main nodes. For the level 5 system to work in this way, however, you also need enough dissimilarity in the system design. So you can't just take the same components with the same software, duplicate it on 2 systems, because if you have a systematic fault, this might destroy the entire system, and both the main node and the fallback node might become unavailable. Therefore, the system design gets more and more complex. So key takeaway here is the higher level of autonomy you want to reach, the greater the design challenges in architecture, software, and safety requirements are. Good. 2 marketing slides that I brought is about the MotionWise platform, and I'll be brief about it. But the main message is basically the system that we designed for Audi scales in a way that it supports level 4, level 5 already today. And it's series proven. It has multiple safety mechanisms that help with supporting these different configurations of a main and a fallback node. It was designed to ASIL level D. So the entire safety platform is designed to the highest automotive grade safety requirements. It supports set decomposition that we just talked about. And it also has an inbuilt deterministic behavior. So things we learned from aerospace and space industry to make a system predictable, control the behavior at all times, is something that is basically in the DNA of the system already. This helps to make it more stable and provide a high availability to the entire infrastructure. And also helps to test the system, validate them, because it's very good to observe and monitor by the end. Little fun fact, some math that we did just for the platform, so a very small footprint software that was delivered to Audi in 2017. We needed to provide 350 documents proving that the work we did was according to the highest ASIL standards. Now, if you would print this out, it would be 40,000 pages that weigh 350 pounds. So that's one huge linebacker, if you want to put it into human terms. And it would stack up 14 feet high. So just to give you a feeling that not only do you need to take a lot of effort into designing these systems, but there's significant effort to be done in documenting that you have done all the work that you claim you want to be doing. So the last 10 minutes I want to use to talk about the next generation of architectures that we see coming. And I realize none of us has a glass ball. At least I knew if I would have one, I probably wouldn't be standing here. But all of that, what we present now, is based on market research, is based on technology roadmaps that we know from partners, but also from other companies. It's based on talks we have with OEM disruptors. So a lot of know-how went into this. And what you see clearly is that safety in the next generation will be the top priority. We talked about level 3, 4, 5 systems needing to be fail operational. Thus, a lot of architectural design work has to be done. Now, if you look at today's cars, some of them have 150 to 200 different electronic control units installed. Some of them just hosting one simple application. Now, if you talk about redundancy and building redundant system, you need to duplicate all this. Clearly, your entire car would be very convoluted with electronic control units and undrivable at one point, plus very costly. Therefore, one of the things that we see happening now in the next 2 to 3 years is the companies changing to a domain architecture. So instead of having 200 ECUs, they reduce the number down to, for instance, 6 or 7 main domains, bordering around smaller ECUs as well. Within these domains, you have integrated several functions, like in the ZFAS, which we discussed with 35 different applications. It could even be more that you're hosting on one domain controller. The reason is, well, first of all, reduction of the components and the need for very close interactions of many of these functions to enable automated driving. So reduce system complexity and enable automated driving go hand in hand here. One of the things, and this is why I think you should be proud to be working in a company like Samsung, is that the semiconductor industry and the advances that we've seen over the last decade, compute power increase over and over again by reducing energy consumption and being very profitable, I mean, or cheap, affordable, that's the word, enabled the domain architecture in the automotive industry. So without the technology advances from companies like Samsung, the domain architecture simply wouldn't be possible. So now, do you connect all these with one another, again, redundantly? So you take, for instance, a PCI Express backbone for heavy data to be shipped around the domains, and then a more deterministic approach like TSN network or other Ethernet network backbone that you can control for critical control data. Now, another thing that changes, where we use new technology as well, is the connectivity in the cloud. So using 5G networks, real-time, with a lot of bandwidth available, the companies are able to introduce new services, like an Uber, like a Google. They always need the ever-on car. And also classical OEMs understood that the car holds its value if you can continue to provide the customer with software updates, with new services, with additional features over the life cycle of the car. Another thing, if we talk about safety as well and automated systems, is that due to the availability of the cloud and the high data capacity, you can add additional sensors, virtual sensors to the car. Talk about high definition maps. So always upload the latest and greatest high definition maps that are available to the car, so the car can compare it to its current location and thus pinpoint the exact spot where it's just been driving on and being more safe at that point. Now, the challenge that we have if we want to get these domain architectures and get the additional features to our customers is that the update cycles of hardware and software are significantly different in the automotive than they are in other industries. Smartphones, they get updates every half year, basically. Software, also in the automotive industry, gets updated very frequently. The car itself takes a long time to develop. If you have a brand new platform, it takes you 5 to 7 years in some instances to get the car on the road. Now, we talked about the semiconductor industry enabling all this change. Now, if worst comes to worst and you pick your semiconductor very early, they might be 2 to 3 years old already. And by the time your car rolls out onto the streets, so you have a brand new vehicle, the hardware inside is 10 years old. So the software that you want to be running on it needs to deal with 10-year-old hardware. Now, if you think about all the applications that you have on your smartphone, if you would like to use that on a 10-year-old smartphone, it would be painful, to say the least, I guess. So, and the same is true for the automotive industry, which today are not accustomed to getting frequent software updates, something that is changing now. But we see clearly that you not only need software updates, but you need the hardware to keep the pace as well. So one of the things that we want to do is provide hardware upgradability for the car. Now, coming back to the 6 domains, what does this mean? 6 domain is great, but they have then limitations, because if you have 6 domains, it's still 6 times the development costs. It's still 6 times where you have to select basic software functions, do the diagnostics, do the tooling. You have sources of software and hardware faults. You have the problems of maintaining each and every single ECU because they might be from different suppliers. You have over-the-air updates that might be very different from each of the single providers. Clearly, the integration efforts as well as safety and security, you have 6 times. And when we talk about fail operational architectures, this means you have to duplicate this effort even more because you need the redundancy in the system. Therefore, I think you get the idea where we want to go, reduce the number to the absolute bare minimum. So just 1. We basically want to build what we call the in-car compute platform, or ICCP. And essentially, the in-car compute platform is a data center on wheels. Now, data centers have been around for quite a while, and similar, like the semiconductor industry, have improved a lot over the past decades. So there's a lot of services and a lot of technologies that are proven in field that we can use, like server consolidation, isolating applications, talking about hypervisors. This is important when you want to run safety critical and non-safety critical applications side by side. So you don't want your entertainment system to go havoc and basically destroy communication between the drive-by-wire or brake-by-wire systems. Another thing that you have is the talk about fail operational availability. So here there's proven and very well-established methods to do all this. You also have load balancing and upgradability that is supported. And we do have reduced energy consumption that goes hand in hand with this, because clearly in the car, you do have very limited resources at hand, and you want to make the best use of it. think about a situation where you're driving on the highway. Why should the parking pilot function be running and consuming energy? So this is something that you can disable in certain driving situations and so forth. And clearly end-to-end security, something that the automotive industry does need as well, as well proven in the field of the data center technologies. But for all the great things that we can learn, there's a couple of things that we do require in the automotive industry that are quite unique that the data center doesn't provide. And since you know the topic of the day, you know that safety is one of them. The other one is hard real time. This comes back to the point I was trying to make with the two software entities interfering with one another. So you don't want that an extremely tight schedule is interrupted, so braking. So, for instance, you detect an object on the road, the system detects it and sends a signal to the actuators to hit the brakes, put in emergency braking. This signal can't be delayed, so we have to make sure that we have that built into the system as well. So in theory, this is what it looks like. You have the 6 domains, and you want to integrate them all into the in-car compute platform. And since we talk about having the data center on wheels, we need redundancy. This means we need 2 of these data centers that are redundantly connected by a backbone system. They're redundantly connected to different power sources, to different sensors, and so forth. So really build a true operational, fail operational architecture. However, you would need to do the same with the 6 domains or 8 domains or the 200 ECUs, but using just one domain, integrating everything into it, decreases the complexity and the cost of the system significantly. So in software, to finish up, it's basically the same. So physically, we put everything in one box, and on the software side, you do the same. You take the 6 domains and all the functions that are behind the 6 domains and put them onto the same platform. Again, here you use a hypervisor technology to isolate critical and non-critical applications so you can run them side by side to one another. Especially for the safety critical applications, we believe that with the MotionWise platform, we have a very good platform at hand that is capable of handling all this. And we would propose that you extend the platform by having very homogeneous management resources, so services that are safe and secure, that we either take from the data center technology, adapt them, or create them again. But the idea is that you have the same services and management tools available for all the applications that are running in the in-car compute platform. And I have to say I'm very proud to be working on this together with the great people from Samsung. This is what the first prototypes look like. And you can see in the overall structure, you have different PCBs that are basically can be replaced like a blade server in the data center technology. So the idea is that without changing too much of the infrastructure, you just take out one unit and add a new computational unit in there. It could be a new processor type that is specifically designed for AI, for machine learning, could be more memory, could be more storage, for instance. So just to give you an idea that this is a way to keep the system up to date and to keep pace with the rapid software development cycles that we see. So I owe you one conclusion before we end. If safety is possible or impossible, I think we all understood that it's possible, and it's a job that takes everyone. So we all need to chip in. Every provider of every system needs to do their part in providing safety to the overall environment. And if we follow structured and standard processes like the ISO, it's comparable in the entire world. And together, we can really advance safe technologies and improve human lives. Thank you.